Well, welcome to our webinar today, our outreach webinar. And we're working on a project called SSbD4CheM, so safer and sustainable by design applied to chemicals and materials. So go to the next slide. So this is our program. We're going to try to cover different aspects of the project in these presentations. So we'll start off with an overview of the project, and then we'll hear from industry. Why is this important in terms of cosmetic products? And then we'll cover a couple of different kinds of topics using modeling, using artificial intelligence, doing the experimental work on characterizing the materials. We'll talk about new approach methods, how we use them in our decision making, and we'll go into life cycle assessment and then finish off with the current insights that we have. So with that, now I hand over to you, Melissa.
Thank you, Barry. So my name is Milica Velimirovic, and I'm researcher at Vito and coordinator of the SSbD4CheM. Next slide, Barry, please. And today I just want to emphasize that SSbD framework has been proposed in order to integrate safety and sustainability in the chemical and product development. And there are like two principles that we have to follow. One is the safety, where we want to ensure that different products and processes do not pose risks to human health and environment. And on another side, in terms of the sustainability, we want to minimize environmental impact and promote resource efficiency through the life cycle of the product. Next slide, please. In terms of the project details, this is for your project where we are with 19 partners from 14 countries, from research institutes, universities, SMEs, and large enterprises. We are also having our three sister projects, Chiasma, Hemat Sustain, and Talkbox, and the most important part are the innovative methods for the safety and sustainability assessments of chemicals and materials, which are developed through the project. Next slide, please. From the side of SSbD4CheM, ambition is first to develop further the framework where new science-based approaches and innovative technologies can proactively identify and address hazards and risks, which includes improvement of safety and sustainability assessment along the product life cycle, having alternative methods for the safety assessment without animal models. Of course, we are also working on the robust, reliable, and faster test methods or models, including high throughput and in silico models, and validated in vitro tools for a variety of substances and materials. By this, we are also trying to collaborate internationally to give industry and other stakeholders uptake of new methods or the models that you will also see today. The next slide, please. Our methodology is quite clear. We have the toolbox, which is equipped with different resources and tools for developing different safe and sustainable products and processes. Of course, you will see today different tools, but we are also producing guidance document databases which have like different properties and which are serving to evaluate the safety and sustainability of the product per se. This toolbox, of course, can be utilized by different stakeholders, industry, government, academia, and civil society. Next slide, please. This methodology is implemented in, maybe next slide, please, Barry. is in three demonstrators. One is a renewable based composite for automotive interior. Another one is development of bio-based self-cleaning water repellent and antimicrobial treatments for apparel textiles. And finally, the nanocellulose for applications in the cosmetics. The next slide, please. In the terms of different products or the demonstrators, already at the beginning, we have different safety and sustainability goals that we did set for instance, in this case, renewable-based composite for automotive interior. Here you see, of course, the new material that it will be used has to be tested in different safety measures, such as the hazard assessment, human health and safety, are also evaluated during the production and the processes of microfibrillated cellulose. What is also very important are the emission of the volatile compounds that has to be reduced by using the new microfibrillated cellulose. Of course, we want to have the reduced formaldehyde release, and of course the odor level target, which is below 3. In terms of sustainability, here you see the list. One is, of course, that we have to have a good mechanical performances, to have the renewable composite formulation with the feedstock content more than 80%. We, of course, want to have the lower environmental impact by 20%, and of course the reduced material weight, which allowed the reduced fuel consumption. When we go to the next demonstrator, which is the bio-based textile coatings, here it's again like several safety goals and several sustainability goals. In terms of the safety, we want to have lower environmental and health impact of our bio-based apparel treatments. Of course, we want again to have minimal VOC emissions, and as every textile or chemical which is new has to comply with the REACH Article 33. Sustainability goals are again the substitution of the fossil-based feedstock, one of the bio-based self-cleaning water repellent properties, of course, the biodegradation in the soil, that has to be more than 90%. In terms of the biopolymer formulations, we have to have different bio-based biomass contact, and of course 20% lower environmental impact by raw material usage and energy consumptions, which are quietly reduced. Coating thickness is reduced. By that we need less material, and of course we want to have like the coating processes that are no energy invasive, and practically the drying steps are less necessary during the material usage, which leads to the small and cost-efficient plant concepts. And finally, when we are coming to the nanocellulose, where you will also hear more from our partners, the safety and sustainability goals, Barry, for the nanocellulose applications are, of course, like one is the skin irritation, then we have like the human health and safety evaluated during manufacture or use of cosmetics products during the process optimization, and of course we want to assess biodegradability and the bioaccumulation of the nanocellulose as one of the safety goals. When we are talking about the sustainability, we are again in the same direction as 3 other case studies. We want to have like the nanocellulose as a material that can be produced from renewable sources. We want to have like the renewable feedstock content of 80%. In that case, we want to have material which is biodegradable, which means that it can break down naturally in the environment and reducing the potential for environmental harm. And of course, nanocellulose can be produced using waste streams from other industries, such as the paper industry, reducing waste and promoting sustainability. From my side, I just want to show you the very last slide, because in order to formulate these three different materials and the products. We have set quite some ambitious goals where we want to involve different innovations in terms of the material characterization, the computer-aided design approach, where we are using computational fluid dynamics, molecular simulation, and machine learning toxicity models to develop further the materials that will be used in the different products. What is very important in the SSbD4CheM is the human health and environmental safety assessment with the different models from in vitro to ex vivo and zebrafish embryos. And finally, we are working a lot on the exposure assessment and risk management, where we are not working only on the reduced VOC emission, but also on the characterization of microfibers and microfibrils released and their fate and the behavior in the environment of all the materials that can end up in the environment, such as the textile after the washing, for instance, or the cosmetic case study. And finally, our main goal is to work on the sustainability assessment across the life cycle. And basically there we have like the dedicated partners that will show also the work on that part as well, and as such have the safety and sustainability together in place in terms of the product development. Thank you all, and that's all from my side.
Okay, thank you. So now we're going to move to a perspective for our cosmetic case study, and I think Zevi, you'll be picking it up now, hopefully.
Yes, hello. So first of all, it's great to be here for all the listeners from the house. We would like to thank you all for the opportunity. I will start, and then Zevi will take the lead. We are from Ava, and in the SSbD4CheM, our main goal is to create a new materials with a nanocellulose. We will talk about the perspective on the application of SSbD to the cosmetic products. Next, please. So what it means, how it can help to the stakeholders, you will see now. Next, please. Yes. So first of all, the industry perspective on the SSbD in cosmetic. We all know that the cosmetics is a mature, very saturated and competitive industry. On the other hand, the SSbD concept is very new, very novel, and as a result, we can see that we need to adjust it and to combine it to bring the SSbD into the market in a sophisticated way. Next, please. Yes, within a sophisticated way to the relevant stakeholders. Next. So in the industry context and the left, we can see very the market realities, and on the right, the success factors that might be. Next. We can see on the left, for example, that first of all, as we know, that the market is very competitive and saturated, and the SSbD is new, we need to know that the strategic stakeholders engagement is essential. The value for the value chain, for the supply chain, and a clear differentiation from the clean beauty claim. Next. So we need to understand that actually the main thing is the consumer. We need to reach to the consumer, and only then we can know what they need, what they want, how they think. from their head, let's go inside of their head, they will think about all the seven pillars in the left, about the safety, about about the quality of the product itself, and on the right, this is actually the secret weapon, let's say, of the industry. Because if you think about it, the industry should know how to deal with the products. It includes the essence of the brand, the innovation, the cultural connection, and the customized personalization. Next.
Okay.
Okay, now Zevi can.
So if we go deeper to the mind of our customers, the basic, after all, is the product's efficacy, how it performs. But this is a must. Today, safety and sustainability are also required by the customers, but this is not enough. And last but not least, and the most important one, is the emotional connection. And we think that customers should really believe in the value and identity if we want to complete the sales and the connection with the new concept. Next, please. After the customers, the second in the priority is the retail strategy, and today actually the market is controlled by the retailers. So we have to find the right partnership or establish the partnership with the ones that are most relevant, as we think is the current clean beauty cosmetics and green beauty could be the first, the pioneers to open the market. Of course, the in-store experience is very important, like education, beauty advisors, and all this information, because it is not a very simple concept, SSbD, and it should be well explained, well educating, if we want to reach success. We think that certification visibility is very important, maybe even must, that will differentiate the SSbD cosmetics from any other green, clean or other good environmental friendly claim.
Next. And another next. Yes. And in the next slide, you will see that also, in the other hand, is all the regulatory engagement. The European Green Deal alignment should be very careful and to align some structure and limitations that will include, first of all, to demonstrate the SSbD compliance with the policies. On the right, to have some standardized certification framework for the SSbD, for example, the COSNOS, that give it some structure and boundaries to the formality. Altogether, this can help and it can support the regulation and to limit the misleading of the clean beauty and chemical-free market claims that happen in our days. Next. And another next.
Okay, so all in all, I think that the competitive landscape should be very seriously studied.
One back, please.
And if we want to succeed, if you could go back one slide, then yeah, I think for success we have to identify all the threats, including the anticipated response of competitors, of regulation. We have to work hard to differentiate our positioning, because SSbD should be differ from any greenwash, false claim of tree huggers or environmental other blah blah blah, to make sure that it will be clear that it is scientifically based and it's serious. I think that innovation should be protected as well, and all this landscape should be thoroughly studied. Last slide. Yeah, last one. Oh, another one. Next, please.
And you can press all of them until you will see the 5 pictures, and we will explain. Another one. Yeah.
Okay, so
One back.
I mean, this should be implemented following the roadmap step by step, and go from the standard, going to the innovation, to establish the innovation, and of course work on the market entry with a lot of collaborations, like for example completing industries like hair products and fragrance, etc., in order to maximize the effect and expand it to all the relevant markets. And thank you very much. Last but not least, last one.
It's the last.
So thank you very much. And here you go to the next industry.
Thank you. Thank you. I think it's very clear. I shift now into talking about how are we using data science in doing this safe and sustainable by design, our experiences last year, this year, and basically the idea is in a first tier approach, try to use all current knowledge and data and bring it together and see what are the answers. And then we can think of the experiments we need to do in the labs to have improved answers. So first of all, if I just start over on the left, it's a workflow. So it's about bringing the information together, and we show you here the workflow software for documenting what exactly have we done? Where did the data come from? What was the decision? And this is coming from a next generation risk assessment project. And here on SSbD4CheM, we're extending the NGRA to also have modules for safe and sustainable by design. There's a lot of knowledge to gather. So I'll show a couple of examples there on how we are building software to help find the data we need. Also very important that this evidence is very well documented. So we have a software there, the methods documentation based on ToxTemp, so that if we do use new approach method evidence, that everything's well documented. And assessment tools, knowledge graphs, won't go into everything, results, comparing the results we get from different databases and different models. So actually, this is our first step, computational workflow. What we actually have to do in terms of working through, looking at an ingredient and gathering the information and seeing in the first step what might be the concerns with regards to hazard. And then in subsequent steps, we look at risk assessment. So occupational, step 2, step 3, we look at consumer risk assessment. And then finally, environmental sustainability and life cycle assessment. So as you see, there's a lot of tasks to go through and do a lot of calculations. So the first one is hazard profiling. So the proposal is look at the existing hazard information. You'll see the tools and databases that we would look at as examples. And if the ingredient really is hazardous, well then don't use it. Use a better alternative. So here I show we're comparing phenol with eugenol. It was a test case we wanted to take a look at in terms of could a bio-based compound be a good alternative for the phenol? And you'll see a couple of things here. So first of all, on the top, I'm showing the data we get from databases, and you can see what we're missing data. So that all the NAs are data we don't have. And the other thing you'll notice here is as well, when we look at different endpoints, we get sometimes answers that are agreeing with each other, and also we get conflicting evidence. So we have to try to deal with that. And so you look at that hazard information, and there's a scoring scheme like you're showing here. And if the substance is harmful, really harmful, then you should not take it forward. However, there may be compounds that have some issues, and it doesn't mean that you have to give up on it completely. So the idea is you score it at different levels, and you see if you can take it forward, maybe mitigate the risk. Now, one complication we have, of course, with our industry case studies is maybe we have models for compounds, but actually in industry, there's a lot of more complex materials used, polymers, and a lot of our models that work for smaller molecules may not work so easily for polymers. So that's a challenge that we're definitely seeing. How do we characterize more complex materials? So that typically involves physical chemical characterization work. So we've built a knowledge infrastructure organizing the images that are generated on the materials in the lab, so that we have all the protocols and data organized nicely, so the data is fair. So it can be organized in a good quality way, and then we can apply our machine learning to the images and do our analysis. So this is an example image repository we've built based on open standards, and what you're seeing here are characterization images from experiments, and then we're looking at are there features that we see that give us a concern on the material or not. So we also are using this is a software we built for risk assessment. So you look at a formulation, the ingredients in the formulation, perhaps also the contaminants, and you do your risk assessment evaluation. So in other words, you look at compositions, calculate your margins of safety, and you make a judgment on the formulation. So here, what we're doing is extending that. Also, you do the safe and sustainable by design steps on the formulations or the ingredients, and do these calculations in a software that's user-friendly and generates your report. This is an example. Basically, we've taken an application which does skin safety assessment, and we compare the results of different models, and then we've integrated that into the risk assessment software I just showed you. So you can bring new approach methods, data modeling results into the risk assessment software and see what the models are saying with regards to concerns about skin safety. And another important aspect of the SSbD is to consider the environment. So this is an example where we're actually looking at the environmental issues in the ingredients, and maybe we should choose an ingredient that doesn't persist for long periods of time. So again, finding a lot of information. So this is an application we built. And basically it goes out and finds the safety data sheets for the ingredients, and then it brings it back and it extracts the data for the ingredients. So I give a couple of links on the slides. So we've made that tool available, and we'll share, of course, all the slides. So you may get a chance to explore a bit later. And this is the documentation of everything you're doing in the SSbD. So at the end, you're going to have an evidence packet, and everything should be well documented, like I showed here. We've also built now a knowledge sharing portal for the project, so all these tools can be used by the different partners to get their work done. And yeah, so this is a very new portal we just opened a couple of weeks ago. But we're also going to share some of these tools and resources with other projects, and try to be helpful for others outside our project. Then, as you'll hear about a bit later, we will be looking at using new approach methods in the SSbD. So this software we've also made available for documenting the test method, and we're going to try to extend it to some new kinds of tests that we haven't worked on yet. So that's also quite, I think, innovative. And I don't really have a time to do a demonstration. If anyone is interested in looking in more detail at one of these tools, we'll be happy to set up a meeting with you and take you through it. But I'm going to take it. I'm going to try to advance the slides, but for some reason now this slide isn't advancing. But the slides will be included, so when you have a bit more time, you can come back and try out some of these resources. But I'm afraid right now that the slides in the Google Drive are just progressing very slowly. I don't know what's going on with the slides. Yeah, it's just slow. Maybe it would have been better to have used the local copy of the slides. All right, here we go. So with that, now I hand over to Andre, who's going to talk about the experimental work in materials characterization.
Good afternoon to everyone. My name is Andre Panag. I'm from National Institute of Chemistry, where I work as a research associate. And today I have a pleasure to talk about some material characterization. Next slide, please, Barry. It's not going to be an extensive information about material characterization, but more like some concept and overviews, how we approached or how you can approach your material and product characterization. So in any material development, we start working with either some ingredients or raw materials. They can be pure chemicals, they can be blends of materials, they can be in form of powders, liquids, sheets or textiles. They are of different origin, synthetic materials, or they can be natural materials. Basically, where most of the information about the material is can be found either in product data sheet or safety data sheet, or if the chemicals are well known, we can find also about some basic chemicals information about databases and literature. Next slide, please. However, when we use those raw materials, we are using them for certain reason. We want to improve some properties of the products. We want to get some better either operational properties, or we want to get better properties of the product itself. We want to improve its sustainability or safety. Next slide, please. As we have many methods that we can characterize materials, we can characterize like chemical properties. So what is the molecular composition of that material or compound? What are the functional groups? What is the purity? If we have some impurities that can influence the performance of our product that we are developing. What can be the reactivity of such material? And here are some acronyms that I'm not going to explain them all, but these are methods that we can use, and they are special laboratory devices, usually owned by research institutes, or for the basic information also by the companies, that we can get information about chemical composition. Physical and physicochemical properties, they tell us some information about, let's say, how the material itself looks like and how it behaves in certain environments. So we might be interested in the size, because nanomaterials are becoming quite popular. They have special performance and special parameters so that they bring to the product itself. So we would like to investigate that. We need information about thermal properties of the materials. We might be interested into the solubility or conductivity of the materials, and many others. So we have also plenty of methods that can characterize this type of properties. And in the end, we have the product itself, so some mechanical properties or organoleptic properties like hardness, some tensile strength, durability, stability of the material, color, smell. They all influence, or we can measure. We have some either standardized methods for that, or for properties that involve senses. We can have some specialist or a special panel of specialists that can evaluate such parameters. Next slide, please. Since this bring like almost infinite options for the combinations of measuring methods and what we can measure, it doesn't mean that we have to measure. The important thing is to know what I actually need and what for. Do I need the information about chemical composition more than it's written in the safety data sheet or in some database? Do I miss some of the data? Do I need those data because I need to know how it's going to behave in my processes, or what is going to be the performance of the product? Or do I need it because of some regulation requires that information? Is it feasible? So can I get this information that I'm looking for with some standardized methods, or do I need some new specialized methods to get me this information? Do I have the instruments? Do I have the facilities, or do I need to get them somewhere else? And of course, as Barry said, we need to consider the FAIR principles. The acronym stands for findable, accessible, interoperable, and reusable data. So these are some principles that we should also consider while doing the measurements, and especially if we are speaking about safety. Next slide, please. So in our case studies, since we had three different case studies, I'll start with the cosmetic case study where we use nanomaterial. Nanomaterial, if we are going to use nanomaterial in our product, we have to consider the REACH regulation. And for that, we need characterization of the nanomaterial in terms of size. And we have many options to do that. We can do it by imaging, by electron imaging. We can do it by atomic force microscopy, and which is the image in the middle, the orange black. And we can get information about distribution, which are the bar graphs on the top right. However, we have partners in our project who are developing multi-angle light scattering. So it's a much faster method that is capable to identify particles in much larger number, so give better statistics about the particle size distribution. And that means for high aspect ratio, as the nanocellulose materials are, in the project there is Postnova who is developing a special light scattering method. And we can also have other methods for analyzing the chemical groups on the top, or we can use imaging for investigation how the cell cultures are affected by this nanomaterial. And we also have methods like measurement of zeta potential or attachment efficiency, which can tell us how stable these particles are, if they keep in the nanoform or get agglomerated, which is also important for the behavior in the environment after discharge of the material. Next slide, please. On the product, it's sometimes a bit simpler because usually we follow some standards and there are some in-house methods for measuring, for example, viscosity by a rotational viscosimeter, measurement pH, which is a basic methodology, organoleptic properties, that means like what is the color, what is the smell, how what is the texture of the material. And importantly, with our nanomaterials, we also want to improve the stability of the dispersions. Next slide, please. In the automotive case study, our selection of the measurement methods was based on what we wanted to know. So we had materials prepared with new additives, bio-based additives, and we want to know was how does it impact our strength or tensile properties, how does it influence the melt flow, which is important for molding. But most importantly, how does it affect total emissions of total volatile organic compounds? So if the new materials improve for operational safety, when you produce this material, this is a pretty important parameter. And that method is based on gas chromatography used with mass spectrometry, where we can get the information about the compounds included in those emissions. Next slide. And for textile case study, where some specific precursor are used and treated with plasma, we are interested what is actually happening with those coatings after this plasma treatment. So what is the composition of the coating? Is it what are the chemical what is the chemical structure, some elemental distribution. And we also can use different imaging methods, specific imaging methods, or again, a mass spectroscopy, which is quite useful technique, not only for information about chemical composition, but also about impurities in our chemicals. And the last slide, Gaberi, please. And on the product, there are two tests being done, or methodologies: water repellency, that is measured by a conventional sessile drop method, where on the picture in the middle you see there is a drop on a textile, and based on the analysis of this specific drop, we can say yes, the surface is more water repellent, and or it's not water repellent, or because the drop spreads. So in combination with all these techniques, we need to first know what we want to measure and then to combine them. We combined the information about the product, and we also combined the information about the substances that we use for developing of this product. That would be all from my side, and I give next presentation the floor.
Very good, thank you, Andre. So let's move into modeling now.
Okay. Hi to everyone. I'm
Hi.
Takis Kolokathis from Nova Mechanics. I'm head of material informatics in Nova Mechanics, and today I will present you material modeling supporting hazard profiling. So as you can see in next slide, okay, here it's a web application that it's called SSbD4CheM, okay, is about a web application for doing a shape by design for skin using a chemical sketcher, smiles, and also provides a 3D visualization. Okay, so here is the ChemFaros database, and where are curated dataset. Okay, curated means that maybe there are datasets that are available in literature, but there are some extra descriptors added on them. Okay, there are also available data from other for other case studies. Next slide. Sorry. Next slide. Wow.
Yeah, I'm afraid the slide set is being slow again. Sorry.
Yes. Okay. Sorry. So I'm waiting to load the slide. Okay. So here, okay, this tool, okay, also there's the ability, okay, not only to use to design a sketcher and smiles, but also someone can upload an SDF file. Next slide. Okay, so we can see there's a chemical sketcher on the left. Okay, also some list of smiles can be imported on the middle. And actually, what's another advantage is that the molecule that is designed through the sketcher can be also 3D visualized through a 3D visualization program at the right. Okay, so next slide. Okay, and the user can select the execute button and select which properties can calculate. Next slide. Okay, so the results they mention the three endpoints. Okay, and also so is if the prediction is reliable. Okay, if it's inside the applicability domain. Next slide. Sorry, no. Okay, so this is very important, okay, because for example, the use of three endpoints is very important because, for example, there are substances, okay, chemicals, such as, for example, nicotine, okay, that they are also maybe are highly toxic, okay, if absorbed through the Delman route. This is about the acute-dermal toxicity, okay, but because potentially causing respiratory failure or death, okay, but they do not cause skin irritation them itself, okay, or skin systematic toxicity, okay. So this is important that to be sure that a cosmetic product is reliable to also investigate these three properties. Next slide, please. Okay. Also, we can increase the accuracy of this model using EGFR the docking models. Okay, using Asclepios 9 nodes. Okay, next slide. Yes, Asclepios 9 nodes includes actually the ligand structure, so it is a chemical that decides the chemical sketcher, and also protein structure preparation. There are, you can see two different pipelines, okay, that they are connected together. This is the right image. Okay, actually, and there is a docking, okay, and the docking score is calculated. Okay, docking score is about is related to the absorption energy of the chemical to the protein. Okay, the epidermal growth factor receptor is considered to be crucial for the skin toxicity. Next slide, please. Okay, this tool is very important because it can be used with other tools developed by Nova Mechanics, such as Titania, okay, with other properties such as solubility, poly points, and etc. Next slide, please. Okay, and except of this tool, we all, during SSbD4CheM, we also have been we develop a nanocomposites polymer builder, where actually someone can design a polymer or a copolymer based on the monomers. Okay, decide also the number of cross links. Okay, and also add the nanoparticle lights here. Okay, this is the tool that we call Hydro Nano Construct. This is a tool for making nanoparticles, okay, when they are in water, because when they are nanoparticles in water, their surface actually is highly interactive and reacts with water, with creating hydroxyl groups, okay, water bonds, and other things. Okay, next slide, please. Okay, so this tool is very important because we can calculate the crystal growth rate of many nanoparticles. Okay, and we define actually how the nanoparticle can be grown, the crystal growth rate of the nanoparticle, based on the surface tension. Okay, this is a silica oxide nanoparticle. Okay, next slide, please. And finally, using this program, we can calculate some descriptors, okay, to enrich a data set, okay, in order to develop a model. And as you can see at the left, we can, in the left image, we can calculate the free energy as a function of the diameter, and to find the most stable, okay, diameter for a nanoparticle. Okay, so this tool now is we're working extended it for cellular nanofibers and nanoparticle. And I think that's the next slide, please. I think that's for me. Okay, thank you very much.
Thank you. All right, so now we're going to move into new approach methods with Ivan.
Yeah, good afternoon, everyone. My name is Yvonne Kohl. I'm senior scientist at Fraunhofer Institute for Biomedical Engineering. And I would like to start with the definition of NAMs. So new approach methodologies can be defined as any in vitro, ex vivo, in silico, in chemical, but also alternative in vivo methods that when used only or in concert with others enable improved safety assessment through more protective and or relevant models and as a result contribute to the reduction or replacement of animal models. So an example of the in vitro NAMs on the next slide. I cannot jump to the next slide, but there you will see that these models can range from very simple, for example, cell line based, up to very complex organ-on-chip solutions. Always important is to follow a tiered approach and combine data. So in other words, to use integrated approach. This brings me to the IATA concept on the next slide. So IATA are integrated approach for testing and assessment, and they combine multiple sources of information to conclude on the toxicity of chemicals or advanced materials. And IATA may include existing information from the scientific literature, along with newly generated data resulting from traditional tox testing methods or NAMs with a goal to fill data gaps. So let me at this point to give you an information on the next slide that there is from OECD. Go to the next slide. Yeah, that there is, if you're interested, an OECD IATA case study project where countries can share and explore the use of these NAMs and interact with each other. So if you're interested, please check the website here. And IATA is based on the AOP concept. And let me explain you very briefly what this is. It starts at a point where we have the molecular initiating event, and this is on the molecular level. This event is then introducing some key events which result in an adverse outcome. So these are different steps from molecular to cellular to organism level, and at each level our different kinds of norms could bring support and test the specific effects. And important is that they are in line, and data from, for example, in silico is then used as a basis for the in vitro models, and in vitro model data is used for the in vivo studies. So if we go to the next slide, maybe during this the question came up if IATA are norms, but I can say no, they are not. IATAs are frameworks for integrated information, and they include data from norms. But as you have heard, we now work with advanced materials, and for advanced materials, we now need to get also further steps to more next generation risk assessment approach where norms are very relevant. So for this next generation risk assessment, which is described in this publication here very nicely, different needs are addressed, and this we also follow in the project here, that we have, for example, to enable the implementation of these norms also in the current legislative frameworks and adapt the current methods of related regulatory guidance to the norms. And very important is also that we have a continuous dialogue and collaboration among all the stakeholders to promote change from risk assessment based on the ethical effects towards more mechanistic safety assessment based on norms. So on the next diagram, you see how this should work in principle, that we first have to define the problem very specifically, addressing also from the synthesis, formulation, use, and end of life. Coming to the next stage for the risk assessment, here we follow also different steps from data gap identification to data acquisition, followed by data evaluation, coming to the risk assessment, and the norms, they could help here for stage 2 for data acquisition. But at the moment, we need to guarantee that the norms are regulatory ready, but most of them are not at the moment, and we would like to bring them and adapt them and bring them to a higher TRL to be used on this regulatory level. So specifically in our project in SSbD4CheM, we develop and improve different norms, and on the next slide we see which of these norms we will bring in 4 years up to a higher TRL. These are different models addressing different organs of the human body, and depending on the exposure scenario in the 3 different case studies of our project, the models are used specifically. So on the next slide, I will show you some details. For inhalation studies in vitro, we use human-induced pluripotent stem cell-based lung models. And for oral uptake studies in vitro, we designed different kinds of chip-based devices for fluidic gastrointestinal models and mucus on chip models. And after the exposure, we studied transport, barrier integrity, inflammation, and viability of the cells. Specifically for the case study cosmetics, as you have heard before, it's more interesting to study the skin contact. And on the next slide, we see here that we use an ex vivo skin model for skin contact studies with different kind of pre-treatment. And here it's very important to assess the inflammation, viability, and apoptosis of the model. And for developmental studies, we have the zebrafish embryo assay in our portfolio of our norms. So on the next slide, we then need to know or need to integrate the data into the SSbD workflow. So why is it important? First, we want to fill data gaps, as mentioned before, in case of new substances which lack, for example, the CLP data, and to do experimental NAMs, for example, also for mixtures where the QSAR are not applicable. So to the other point is to prioritize new chemicals in early design phase and assess the relative to benchmark in parallel to technical performance. So we need these norms and the data to support safe materials from early design phase to the product application. And on the next slide, I would like to give you again the information that we therefore need fair data. What does it mean, fair data, to optimize the reuse of data? Is we need findable data, so it should be included in searchable repositories. We need accessible data, so the data should be open available. We need interoperable data, so we need standard vocabulary, and the data should be reusable, so we need reproducible workflows and protocols which are also available. And I would like to end up with one example how NAMs could be used for SSbD. This is a publication where our colleagues of the SSbD4CheM consortium were also part of, and here the goal was to find a safer and renewable material for bisphenol A. So BPA, we all know that we have to replace it. And what did they do? In the first step, they did some in silico analysis based on the chemical structure and the chemical properties. And the result was that they identified one structure with structural analog to the BPA. And in the second step then, this analog was tested in vitro. And we see some results of this on the next slide, because here the controls, the 17 beta, as well as BPA and BPF, they fully activate the human estrogen receptor. So they make a very intensive hormone reaction. But on the right side of the diagram, you see the new alternative substance, the bio-based alternative, which did show slower estrogenic potency. So this is a quite nice example that you should use NAM-based screening prior to high-tier testing. And this is the way how we should go. And yeah, this is my final take-home message for you. And I hand over to the next speaker.
Thank you, Yvonne. Might just need a second to get for the slides to move. Okay, so now we're going to move on to the topic of life cycle assessment with Niels.
Yeah, thanks, Barry. I'm Jens Thunemann. I'm an assistant professor at Leiden University in the Institute of Environmental Sciences, and here I mainly work on life cycle assessment and specifically prospective life cycle assessment and how that is integrated in SSbD. You can go to the next slide, Barry. So first of all, what is life cycle assessment? I can also start without the slide. There it is. So what is life cycle assessment? In general, life cycle assessment is a method which is used in SSbD to assess environmental impacts of services and products. Products could be, for instance, a part in a car. I will come to this example later because it's one of the case studies we analyze in the SSbD4CheM project. While LCA is a very general framework, and its use and application is also standardized in ISO norms 14040 and 14044, and it usually consists of these 4 phases you see on the right hand side of the slide, which is a goal and scope definition. In that phase, you first of all state the aim of your analysis. So it could be from a basic comparison of part A with part B, but also it could go into an eco-design where you want to improve a certain part in accordance with environmental impacts. So there you then specify the aim, then also the scope. Scope means usually you want to assess impacts from cradle to grave, meaning from extraction of raw materials to the end of life, for instance, recycling. But there could also be other scopes, like, for instance, cradle to gate, if you're a company interested in your specific impacts, which end usually at the gate of your factory. And then you go into the next step, which is the inventory analysis. In inventory analysis, you gather all the data for the processes. You want to assess these processes, or this data you gathered is then assessed in the so-called impact assessment phase, and then you interpret. You also see this multiple errors between phases, meaning LCA is inherently iterative, which is of course important also in the realm of SSbD. And I will come to the specific application of lifecycle assessment in SSbD a little later. What is important is that we usually look at a lifecycle perspective, meaning we have a comprehensive look at processes, products, and services, as said, usually from cradle to grave. Why is that important? Because we can then discover trade-offs among different processes or even impact categories. And impact categories, what could that be? The most prominent impact category, for instance, is climate change. But it could also be abiotic resource use. How much resources are you using in your product? While there's also other stuff like water use, eutrophication, acidification. So it's not only about climate change, as we also look into other environmental impact categories. So you can then discover trade-offs among lifecycle stages, but also impact categories. So how do we apply that then in the SSbD frame that is visualized on the next slide? Which is usually LCA and SSbD, we apply it ex ante because we usually work among engineers and product developers, which usually are in the development phase of a new product or service or good whatsoever. So that is important to understand that we actually do not know how the final process usually looks like. So we also need to work with a so-called ex-ante toolbox, mimicking a futuristic system. For some products that might be easier than for others, think about an airplane, which usually has an innovation cycle of 25 years. Then, of course, you need to look further into the future, while in this SSbD4CheM project, we're looking into products with a shorter innovation cycle. So then you maybe look into a future of 5 years or so. But still, that is important to understand that this is a futuristic prospective assessment, we call. And SSbD as you know, it's a tiered approach. That also then is important to understand that we then also need to apply LCA in an ex-ante and tiered approach, as stated on the slide. That is somewhat challenging for LCA practitioners because the conventional pathway of decision making usually is that we first identify a problem, we formulate alternatives, so there's alternative A and alternative B, we analyze them, and then we select an alternative, right? As easy as it is. But in SSbD, it's usually that it's evolving over time along the innovation cycle, that we get new information, we get new insights, new data. So we need to go tier by tier and in an iterative manner to then analyze and then in the end select the alternative, which makes most sense from an environmental perspective. So it also needs a different mindset to use LCA and SSbD. This is very important to take that in mind. And then I will come on the next slide to an example of this. You already heard about the example of the car part. Can you go to the next slide? Great, thanks. Here we did a cradle to grave analysis for a prospective LCA about 2 different parts. On the left-hand side, you see the system boundary, so the system we're analyzing for the use of a car, once using a part which is used in the car, which uses a talcum PP compound, while on the right-hand side, you see we use the same system, but in this case, we use a softwood PP compound for this specific part. So that is the main difference, that we have a car either using the talcum PP and the softwood PP. Why is it important to to also have the application in mind. This is very important because you could think of weight differences between the parts, right? Weight differences would then, in the use phase of a car, result in less or higher fuel demand. So this is important and also very nice of the SSbD framework, that you not only look into chemicals or formulations or singular products, but in the application, because for LCA that might make a difference on the full life cycle perspective, and that is what we are interested on the whole life cycle and the whole environmental impacts across this life cycle. So that is why we are not only looking in this part, because that could also lead to false conclusion, but in the full application. And how does the result look like? You see that on the next slide. When we compare these two things, you see I will mainly go and discuss the bottom left figure. So what you see here is the climate change impact, so measured in kilograms CO2 equivalents per functional unit. So driving this car over 150,000 kilometers, and what the differences are when using the PP or the PP part, either with talcum or softwood. And the alternative A1 is the one with talcum PP, and the alternative with A2 is the one with softwood PP. And what we did is we also analyzed different modeling perspectives, because we said usually you have this conventional LCA perspective where you time integrated assess impacts at one point in time. But usually you know that this is not true. Usually we have the production maybe today, you will build a car tomorrow, you will drive the next 20 years, and then you will have the end of life in year 21, right? This is the so-called time explicit modeling perspective. And then we have a so-called prospective static assessment, which would be the assessment of the environmental impacts in 2020. And we were interested, like, what additional insights we could get from this perspective. And surprisingly, at least for this marginal change in the car, we couldn't see diverging conclusions, because you see that when you compare the near present static impacts among each other, they do not lead to a different conclusion than that the softwood PP alternative, at least from a climate perspective, performs better. So we concluded, at least for this specific case, there is no real difference in modeling approach. It's also good to know. But on the other hand, we also get other insights from that. For instance, that we see that the results are mainly driven of the high impact of the PP compound, which is of course important, and that weight reduction is also important, at least for the use phase to some extent. And then we see, in addition, the blue bar of the stacked bar chart represents the end-of-life scenario. And end-of-life scenarios could also vary. So you could imagine that the compound gets incinerated or it gets recycled. So there is also something to be investigated, which we already did, but I'm not showcasing that today. So this already shows the impact of LCA within SSbD, and with these results in the very early stages, we can already guide then the decision makers and the engineers developing this product to further look into this production step, but also in the end of life step to improve recyclability, for instance. Well, then I would like to conclude with my last slide, Barry. And on that slide, I'm just capturing what LCA adds to SSbD. So it gives you some qualitative and quantitative insights into the broader system. As we said, we are mainly looking into the application perspective, not only into the material perspective. We also leverage the use of deep uncertainty thinking. Sometimes we more working with probabilistic spaces, so integrating distributions of parameters for unknown variables in our systems. And specifically with that, also having this, we call it ex-ante toolbox, for instance, which I just showcased with the time explicit modeling. We can already highlight what is needed from a modeling perspective, which also I think is very important for the SSbD frame in general. That's about it. Thanks, Barry.
Thank you. All right, and we have one more to go, and Yvonne is going to finish for her with the current insights we have from our case studies.
Thanks a lot, Barry. I hope you can hear me well. It's also
Yeah,
my
yeah.
pleasure being here today. Thank you. So my name is Ivana Burzic. I'm international project manager at WoodK Plus from Austria, and the role of WoodK Plus in this project is the leading of the work package related to the case study. So I give my best in the next 10 minutes to give you the most important highlights from the achieved results. So when we go to the next slide, it's a first thing and very important input for any project definition, targets and objectives, clear objectives. So this is what we did. So for these different case studies that we do cover here, addressing different materials for the textile, also for the cosmetics and automotive applications, first target is dealing with the development and validation of at least 2 wood plastic composites. We do have a target, as we learned at the beginning of this event, that we have to fulfill some optimized TVOC emissions, heavily important for the automotive sector. And besides that, also looking at odor and also improved environmental impact of these materials when we do a prototyping of specific interior car trims that will be selected. The next target is related to the textile field. So here we also set a target of that we want to achieve at least 2 different organic monomers for the application using atmospheric plasma polymerization. They should have capabilities of self-cleaning and water repellency, but also providing some antimicrobial performances for the textiles that are provided from our industrial partner. For the cosmetic case study, here we are testing different nanocellulosic materials. So here, in respect also to the SSbD framework, that's a very complex task to do. And we cover basically and testing different nanocellulosic materials, addressing the needs from different cosmetic products like face cream, body lotion, facial mud mask, but also some other applications of the Dead Sea mud. Of course, since this is a bit lower technology readiness level project, but we will still go to the prototyping phase, targeting technology readiness level 5. So all the materials that we are producing here, we are prototyping and also addressing the needs of the predefined key performance indicators that we have per case study. The next slide is focusing on some highlights from the automotive case study. So here, so if we move Barry to the next slide, it's just a title, I think. Coming, yes. So in this value chain, you can immediately go to the next one. It is worth of mentioning that in this value chain, it's very simple one. So we are closely working WoodK Plus on the material side with our end user, CRF from Italy, addressing, of course, different KPIs, as mentioned before, for automotive sector, interior of the car. And CRF is an R&D of Stellantis Group. So how we cooperate with other work packages, we learned today how many different safety and sustainability tasks and models we include here in this work. So starting from the work package 3, where we do different TVOC emission testing, but not only that, following the standard ISO standards VDA 278, for example. We are also in parallel developing a new method using some more advanced methodologies to do a fast screening of the TVOC emissions, not only focusing on the sum up value of the TVOC, and that is being used to simulate potential exposure not only on the workers during the production of such materials, but also in the end use phase that is later on linked to the risk assessment. Besides that, as we learned also today from the presentation of Fraunhofer, there are also novel models, non-animal models developed here that will be also applied in this case study and combined with the consumer exposure. Where we obtained data gap, definitely then we apply different modeling and different tools to fulfill the data gaps. And at the end of the day, we also take care nicely on the data management, because you may imagine how many different data from one to another task may take place here. The next slide is to show you that some results starting from wood plastic composite, starting from the processing side, it's worth of mentioning that there are different matrices being covered here. On the polymeric side, renewable PP, then some other polypropylene compounds targeting very high impact strength. Recycled polypropylene is also taking place here. On the side of the sustainability, to replace standard mineral filler compounds, we are implementing different cellulosic fillers, regenerated cellulose, ultrafine cellulose, but also softwood and hemp fibers. The processes are already state-of-the-art here, so we start with the compounding injection molding for the prototyping, and as mentioned before, addressing all the needs when it comes to safety and sustainability. The next slide is showing you some selected results for the event today, more covering the mechanical results on the testing of injection molding from the wood plastic composites. At the first row, you can see our target, basically the reference material that is being selected from the CRF Italy. And we highlight here the most, so the recent results that we have, the best performing, covering different targets, impact strength, flexular modulus, and tensile strength. Also very important when it comes to processing, as everyone knows, going to injection molding from lab scale to the big scale, melt flow index is there to be considered for sure, and addressing the flowability, but also thinking on the sustainability targets. We also like to work with lower density materials, and we can see here that by implementing cellulosic fillers, we can benefit exactly starting from there. The next slide is to show you some results on the TVOC emissions. So here, as mentioned before, okay, so first weathering testing, as said before we prototype fully the interior car trims in parallel with the material development and looking at the mechanics, definitely we have a look on the weathering testing, because different levels of irradiation are being applied, and that would guide us further besides mechanics achieved, that we select properly where such materials can be nicely implementing, because that's also next important aspect for the automotive application. So the next slide is dealing with the TVOC emission results, and this is basically where we combine the work not only on just measuring and following VDA 278, which is rather common for the automotive industry. There are also some others different from Europe to the USA region. We are using method development, so coupling some micro-emission test chambers available at Woodkey Plus with proton transfer reaction time of flight instruments available from TOFWERK from Switzerland, and that supports us basically in our work that we can obtain faster and simulate the potential exposure of the consumer during the time of 4 hours, not only just measuring the total TVOC value as sometimes needed, because this is still safe by design project. On the next slide, I think now we move to the textile case study, so please move on to the next one. Here, value chain is being covered with 2 R&D, CTCR from Spain, but also coating team of Woodkey Plus, nicely working together with the textile end user Cortex from Turkey. So, and here again a similar slide I showed you for the automotive, definitely for this case study where we developed different antimicrobial and water repellent coatings. We have a need for a little bit different analytical tools that we basically check the chemical composition of our coating after application of atmospheric plasma. That was mentioned before, so I won't go to the detail. And then the work is very similar compared to the previous case study. We go to VP4, where we basically simulate and using some here developed models to have idea on the potential worker exposure, but not only on that, also when it comes to the consumer and end use phase. Life cycle analysis, as mentioned in the previous presentation, is of course guiding us further when it comes to the sustainability. The next slide, please, is showing you more details. Since we are a bit on the time limit, I won't go too much to the detail, but as mentioned, in this textile on the side of the coating development, as you can see, we also achieved and developed different, selected at first, different precursors as listed here that are being applied by plasma. Of course, when it comes to any processing, we take care that we screen different processing parameters as shown here on the left-hand side in the table. And for some candidates, we already achieved hydrophobic coatings for standing alone precursors selected, but also being combined with some other. Homogeneous thin film obtained on the textile is very important, looking on the practical side and industrial application. And as you can see, as mentioned before, we also take care simulating how different media, if I may say so, like water, milk, and also some stains may behave once they come into contact with the coated textile. So very nice results. So we are not yet there with achieving all performances, but I would say in a good way. PFAS is basically something that is here a benchmark and something that we would like to replace in the future. So the next slide is showing the results on the antimicrobial activities. So here we talk still about different substances, and among different tested within the project, acrylic acid showed already some very good, strong antimicrobial activities once quoted on the PET textile. But of course, there is still work to do, of course, combining different materials as shown here. We are also, as mentioned in the presentation of Andre, we are also developing deep transfer method, basically how following ISO standard, how we can adapt and test antimicrobial activity on the textile. Of course, the benchmark is here silver to be replaced because, yeah, we learn from day to day that there are also some different and new safety measures when it comes to such materials. For the closing of this presentation, I would like very shortly to talk about cosmetic case study. So next slide, please. Is where we already heard the presentation from Ahava today, and also from, again, from Fraunhofer, that we also apply non-animal models when it comes to cosmetic case studies. So this is how we basically validate as well our models that we develop. So similar scheme we designed all together that we show how we combine the different activities within the project, from the analytics to the modeling, as shown before, but also when it comes to the safety assessment and potential exposure of the workers, but also consumers. Next slide, please, is showing you some highlights from the tested materials. So we really work here with almost any existing crystalline nanocellulose materials available at pre-commercial, but also at commercial scale. So if we move to the next slide, please. I still do not see the changes. Yes. As you can see, as I just mentioned, so we tested the different CNC and CNF, so cellulosic nanofibers, that are, of course, being combined, addressing the needs of the specific cosmetic products. Colleagues from AHAVA, together with National Institute of Chemistry, are working on different products like face cream, SPF lotion, facial mud mask, and Dead Sea mud. If we go to the next slide, I show you just some highlights that, of course, each product, cosmetic product, has some specific needs and specific concentration that needs to take place here. So as we can see, for some candidates that are screened in this project, stability, that is very important aspect for the cosmetic products, is being achieved already. And for the facial mud mask, some candidates already fulfilled that, for example, but some, of course, are still under evaluation, so to speak. Next slide is showing still two other products that we cover within the project in this task, and that's a Dead Sea mud. Again, as mentioned, we take care on the future consumers, so we always check how the filling, so basically how the new additive may impact the texture, but not only that, also the appearance and anything that matters to the final product. And these are just some examples from the tests that are being done on the colleagues at the AHAVA laboratories. So next slide is, I hope, conclusion slide. So this is just to try to summarize all what has been said today. As you can see, this is not a typical R&D project focusing only on the material development. Along doing this, we need to take care addressing different safety, but not only, also sustainability targets that we set. And for each specific case study, as written here, we already developed some good candidates achieving the KPIs per case study. What is next to come? To test further and validate all the models, as very important for our future non-animal models to test, starting from the cosmetics, but also being validated for another application fields like textile and automotive. Of course, the technology and the method that is being at the moment applied only to automotive sector, that's special fast screening of the TVOC emissions. We would also at a later stage in the project apply to the textile case study, for example. To close my presentation, I still would like to invite you to follow us using different, yes, thanks a lot. So using different so starting from the web page, but also using LinkedIn, Zenodo, and YouTube. So we are happy to get in contact with you. I think we might have a short Q&A session. I thank you a lot for listening today from my side, and happy to be with you today.
All right. Well, thank you, everyone, and look forward to getting some feedback.